Water. There's one word for it, but two ways to describe it. There's water we drink and water we can't drink. More and more of us are consuming this drinking water, which represents only an infinitesimal part of the resource available on Earth. In 20 years, 47% of the world's population will live in areas subject to serious water scarcity. And yet, 40% of us live near the coast. What if getting a mouthful of seawater could one day become enjoyable? What if we could actually drink seawater? Let's see how this is possible. To protect the marine ecosystem, seawater is pumped at a speed 3 times slower than a fish swims. This water is then filtered to remove all particles such as algae and sand. After this stage, only molecules of water and salt remain. The salt water is then sent at a very high pressure through an extremely fine membrane. The pressure exerted on the water during this process is equivalent to 100 elephants standing on a manhole cover. This is called reverse osmosis. The energy produced by this process is partly recovered and reused to operate the plant. For every 2 liters of salt water pumped, we obtain 1 liter of pure and demineralized water. The other liter of water, called brine, is twice as salty. After being treated and diluted, it is returned to its natural marine environment. The pure water is enriched with mineral salts essential for human health. And the water is then distributed in the drinking water network, all the way to the tap. Today, more and more plants are desalinating seawater, providing certain countries with nearly 60% of their drinking water. Desalination is a solution to meet the 21st century's water requirements. In 2015, desalinated water will already represent more than 2% of water consumed, and thanks to research and innovation, the technology is improving every day.
Welcome to E.6.3. Today we're going to evaluate the process to obtain fresh water from seawater using multi-stage distillation and reverse osmosis. Fresh water is becoming an increasing concern among governments, and they're trying to put in a lot of plans to safeguard the future of fresh water. And that's basically because although we do have lots of water all over the planet, the problem is a lot of it on land is now seemingly increasingly polluted, and so it needs to be treated. But in terms of the focus here of seawater, we can't drink seawater because seawater contains a lot of salt. And so when you drink salt water, actually the water in your body has a lower concentration of salt than what you just drank. And in nature, the process is that water will go towards wherever the higher concentration of salts or other compounds is. So actually the water is going to leave your body to try and lower the concentration of the salt water you just drank. So even though you're drinking water, you're actually drawing it out of your body. So this is the process, or the problem I should say, that we have to remove that salt. So let's see how that works. The first one is called multi-stage distillation, and just to briefly walk through that in this quick diagram here, down here you're going to have brine. Brine is another word for salt water. And so you heat it up until it vaporizes or boils, and then the vapor goes up and it will touch a colder coil here. So the surface will be cold, and then the water will condense, so change from gas to liquid, condense, and then drip down, and it can be collected. So when this happens, only the water goes up and the salt stays in the brine. So this is a way of separating it. You can see here that it's sort of designed that as the water that is cool is coming in, so that this is cold, it will actually absorb heat during the condensation process. So when something's changing from gas to liquid, it has to lose energy. So it gives that energy to this cooler water inside the condenser. And then when it leaves, it has warmer, it's gotten warmer. So they sort of try to recycle that energy to try and make it a bit more efficient. So what basically happens in 3 steps is seawater is heated to its boiling point. Pure water then condenses on the condenser. and the heat given off by the condensing water will save energy as they recycle it in the system. Our second system is a reverse osmosis. So first, to look at one of the root words, osmosis, that is the movement of solvent, but we're going to focus on water, from dilute to concentrated solution. And so that's what I was talking about in our body when we drink salt water. The water from our body travels in to try and dilute that salt water we just drank. So that's the natural flow of things, from less concentrated to more concentrated, to dilute the more concentrated. So to visualize this one here, sorry, the computer's being a little slow. There we go. Okay, so sorry about that. There we go. So this is what we call reverse osmosis. So you basically have water that is separated by what we call a semi-permeable membrane. And basically what that will allow is it will allow water to pass through, but it won't allow the ions, for example, like the sodium and chloride ions that make up salt water, to pass through because they'll be too large to fit through the holes. So that's why we call it semi-permeable. Permeable means it allows to pass, semi means some, so it only allows water to pass through. Now you'll see here that as it's set up, because there's a high concentration of salt water here and a low concentration or none here, the actual natural flow would be towards the left. Water would actually want to flow into this side to dilute this. So in order to make it go against the natural order, what we do is we add pressure. We squeeze it down so that the water has to, can escape through the holes. So we're sort of pushing it down so that it has to go through the holes. Otherwise, it would go the opposite way and we wouldn't get our fresh water. So we can remove this and drink it now, and then the ions stay over there. So to summarize that, basically your salt water is given a high pressure. Now depending on the book you take a look at, this number varies widely, but in a previous question this was one of the stated numbers that they would accept. So I've put that here, 70 atmospheres. So in other words, 70 times atmospheric pressure. They use a semi-permeable membrane. That grammar is not good there. All right. So there is we'll just put there's a semi-permeable membrane that allows water but not the solute particles. Solute means the solid that was dissolved, so in this case the salt, the sodium and the chloride, particles to pass through. The water passes through, leaving the salts behind. And you just want to note here that there's actually a high energy cost to achieve the pressure needed, so it's quite expensive. And multi-stage is also, very energy intensive, which is why we have this problem of, yes, we can make fresh water, but the energy to heat the water to boiling point, or the energy to create this pressure, has to come from somewhere. And right now, pretty well, most of our sources of energy are not clean sources. They're sources that produce carbon dioxide. So as a result, by cleaning your water, you could still be contributing to the greenhouse effect. And so we have to figure out how to solve that problem. And there are definitely some technologies on the horizon that make use of solar to help do some of these processes.